So hello. So we are going to start the topic today: electric charges and fields, JEE PYQs. So let's start the topic. Disclaimer: the images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. Okay, so our first question. Two isolated metallic solid spheres of radii are two isolated metallic solid spheres of radii r and 2r are charged such that both have same charge density sigma. The spheres are then connected by a thin conductive wire. If the new charge density of the bigger sphere is sigma prime, the ratio sigma prime by sigma is. And your options are 5 by 3, 9 by 4, 4 by 3, and 5 by 6. So I will give you some time to review the question. So the answer is fourth option, which is 5 by 6. So let's come to the solution. Using concept 1.4, given charge densities are equal. We are given that charge densities of both the spheres are equal. Now, sigma is q1 by 4 pi r square equal to q2 by 4 pi 2r square. Means the charge densities are equal. This means the q1 by 4 pi r square means for first sphere and q2 by 4 pi 2r whole square is for second sphere, where sigma is the charge by area. So by solving this equation, we will get 4q1 equal to q2. Now, charge on bigger solid sphere after connection. Okay, we all know that when we connect two metallic solid sphere that are charged with a thin conducting wire, the potential on the surfaces of both the spheres becomes equal. So what is the charge after the connection on bigger solid sphere? We will find. So since potential becomes same, potential of both the solid sphere becomes same, we can write, we know that the potential formula for potential on the surface of a charged metallic sphere is kq by r, where q is the charge on the solid sphere and r is the radius of the solid sphere. So here, because both potential on both the surfaces of solid sphere is equal, so kq1 prime upon r1 is equal to kq2 prime upon r2, and mark this as equation 1. So according to conservation of charge, now we are connecting both the metallic solid sphere with a thin conducting wire. So charge will transfer from one solid sphere to another to balance, to make the potential on both the surfaces equal. But net charge on both the metallic solid spheres remains conserved. Means the charge after the transfer of charge, net charge after a transfer of charge from one sphere to another sphere is equal to the net charge before the transfer of the charge. Means q1 prime plus q2 prime is equal to q1 plus q2. Now q1 prime is equal to q1 plus q2 minus q2 prime. Put this equation as 2. Now put 2 in 1 and solve it. after putting 2 in 1 and solving, we will get this type of equation. Q2 prime is equal to total charge. QT is total charge into R2 upon R1 plus R2. R2 is the radius of second sphere, that is 2R, and R1 is radius of first solid sphere, that is R. Now put these values of radii of both the solid spheres in the equation. We will get Q1 plus Q2, that is total charge, and 2R upon R plus 2R. Now after solving, we will get 5Q1 into 2 by 3. Now sigma prime. Sigma prime is the surface charge density of bigger sphere, which is equal to charge on the bigger sphere after the transfer of charge, after connecting it with the wire, thin conducting wire with other solid sphere, which is Q2 prime upon A2. Q2 prime we have found 5Q1 into 2 by 3. And A2 area of bigger sphere is 4 pi 2R square. But also we know that Q1 is Q2 by 4. We have to find the sigma prime in the terms of Q2. So putting Q1 equal to Q2 by 4, we will get sigma prime equal to 10 by 12 Q2 by 4 pi 2R whole square. Now we can see Q2 by 4 pi 2R whole square is the surface charge density of bigger sphere before the transfer of the charge, before connecting it to other sphere by thin conducting wire. Q2 by 4 pi 2R square is the initial surface charge density of the bigger sphere, and sigma prime is 10 by 12 into Q2 by 4 pi 2R square, which will eventually becomes sigma prime by sigma. We will get 10 by 12, and after reducing it to 5 by 6. So the answer we will get here is 5 by 6. I hope you understood it. Okay, let's move to the next question. 64 conducting drops, each of radius 0.02 meter and each carrying a charge of 5 microcoulomb, are combined to form a bigger drop. The ratio of surface charge density of bigger drop to the smaller drop will be. Now 64 drops we have of radius 0.02 meter and each drop is carrying a charge 5 microcoulomb, and they combine to form a bigger drop, and now we have to find the ratio of surface density of bigger drop to the smaller drop, and your options are 1:4, 4:1, 1:8 and 8:1. So I will give you some time to review it or think about it. Okay, so the answer is option B, 4:1. So let's move on to the solution. Using concept 1.3 from law of conservation of charge. Now, conservation of charge applies here. When the charge on each drop is 5 microcoulomb and they combine to form a bigger drop, the charge before the combination, net charge before the combination of on each drop and the net charge after the combination will remain conserved. That is 64 into small q. Small q is the charge on the small drop, that is 64 drops. So 64 into q is the net charge before combination equal to capital Q, that is charge on bigger drop after combination. So charge will remain conserved. So capital Q by small q is equal to 64. That is the ratio of charges of both the drops. Okay, now volume also will remain constant, means conserved, means volume of 64 drops small drops before the combination combined is equal to the volume of large drops, because they are combining to form the bigger drop. So volume of n small drops, n here is 64, equal to volume of large drops. So 4 by 3 pi capital R cube, capital R is the radius of bigger drop here, equal to 64 into 4 by 3 pi r small r cube. So 4 by 3 pi small r cube is the volume of one small drop, and into 64 is 4, because 64 drops are combining, so volume of 64 drops is equal to the volume of bigger drop. So after solving, we will get R, capital R is equal to 4R, means the radius of the bigger drop is equal to the 4 times the radius of smaller drop. And the ratio of smaller drop, radius of smaller drop to the radius of bigger drop is equal to 1 by 4. Now, we will now calculate the ratio of the surface charge density of the bigger drop to the smaller drop, which is equal to Q by 4 pi r square. R here is capital because we are considering the area of bigger drop, and capital Q is charge on bigger drop, upon small q by 4 pi r small r square. That is surface charge density of the smaller drop, equal to Q by capital Q by small q into small r by capital R whole square. So this is the simplified equation. Now we will put the values. Now Q by Q. What is the ratio? We have found Q by Q. We have found earlier 64, and the ratio of small r to capital R is 1 by 4, and the square of this is 1 by 16. So we will get the ratio, final ratio of surface charge densities is 4:1. I hope you understood. Let's move on to the next question. A 10 microcoulomb charge is divided into two parts and placed at 1 centimeter distance so that the repulsive force between them is maximum. The charges of two parts are. So 10 microcoulomb charge, we have divided the 10 microcoulomb charge into two parts, means 5 microcoulomb charge, and other one is also 5 microcoulomb charge, and we have placed them at a distance of 1 centimeter so that the repulsive force between them is maximum. The charges of two parts. Okay, 5, this is the one combination, 5 microcoulomb, 5 microcoulomb. But we can divide, there is not written that equal parts. So we have to find the maximum charge. So what is the maximum force? How we will divide these charges, two charges, that the force become between these charges when placed at 1 centimeter distance apart becomes the maximum. So options are 7 microcoulomb and 3 microcoulomb, 9 microcoulomb or 1 microcoulomb, 5 microcoulomb and 5 microcoulomb, and 8 microcoulomb or 2 microcoulomb. 5 microcoulomb and 5 microcoulomb is the one option which I have assumed earlier, but it might not be the answer, or it might be the answer. So I will give you some time to think. Okay, the correct option is C, 5 microcoulomb, 5 microcoulomb. Okay, solution. Using concept 4.1.1, divide charges Q equal to 10 microcoulomb into two parts. So we are dividing this charge into two parts. So we don't know that we have to divide equal parts or we have to divide it into unequal parts. So we'll see how we'll do this. So let assume Q1 equal to X and Q2 equal to Q minus X. Means we are assuming Q equal to 10 microcoulomb, and we are assuming that the charge we have divided into two parts, and the charge on first, we have first part, the charge is X, Q1 is the charge on first part, that is equal to x, and q2 is the charge on second part, that is q, that is the total charge, minus x. Now force between these two charges is k into charge on first part into charge on second part, that is q minus x, upon the distance between them, r square. R here is 1 centimeter. So this is F equal to k x q minus x upon r square. So for F to be maximum, now we know that F to be maximum, what is the condition? If we want the condition for F to be maximum, that is derivative of F with respect to the charge x, means df by dx should be 0. That is the condition, that is the way to find the condition of force to be maximum, that how we will divide the two charges, in what way that the force between them becomes the maximum. That is to find the derivative of F with respect to charge x equal to and equal to it 0. Now after solving, after taking derivative, after differentiating it with respect to charge, we will get q minus 2x equal to 0. So from here we will get x is equal to q by 2. That x, q1 equal to x, means the charge on the first part should be q by 2. Means what is q here? 10 microcoulomb. So the charge on first part should be 5 microcoulomb. And also we can find the charge on second part, which is q2 equal to q minus x, and q is 10 microcoulomb minus x. X here is we have found 5 microcoulomb, and the charge on second part is also 5 microcoulomb. So the force between them will be maximum when we divide it into equal parts having equal charge. So option C is correct. I hope you understood. So let's move on to the next question. Two uniformly charged spherical conductors A and B of radii 5 mm and 10 mm are separated by a distance of 2 cm. If the spheres are connected by a conducting wire, then in equilibrium condition, the ratio of the magnitudes of electric fields at the surface of the spheres A and B will be. So there are two uniformly charged spherical conductors having different radii and they are separated by 2 cm. If the spheres are connected by conducting wire, again the similar question, when we connect two conducting sphere with conducting wire, then it will, the potential on surfaces of both the spherical conductors becomes equal. So then equilibrium condition, what is equilibrium condition? Potential becomes same on the both the surface of spherical conductors. The ratio of the magnitudes of the electric fields at the surface of the sphere A and will be. Now we have to find the ratio of magnitude of electric fields at the surface of spheres A and B. So your options are 1:2, 2:1, 1:1 and 1:4. So I will give you some time to think or review the question. So the option, correct option is B, 2:1. So let's move on to the solution. So using concept 16.12.1, from the question, when the charged bodies are connected, potential becomes same, which I have already mentioned, that when we connect two spherical conductors with the conducting wire, the potential on surfaces of both the spheres becomes equal. So VA, the potential on the surface of A conductor, equal to VB, which is potential on the surface of B conductor, which is equal to KQA upon RA equal to KQB upon RB. This is the formula of potential on the surface of spherical conductors. That is KQ upon R. R is the radius of the spherical conductors. So by equating them, now we know that the value of K is 1 by 4 epsilon naught. And the value of K will cancel out from both sides. We will left with QA upon QB equal to RA upon RB equal to 1 by 2. So this we will get the value of ratio. Ratio of two charges, ratio of two radii is equal to 1 upon 2. Now electric field at the surface of conductor A. Now we know that formula for electric field on the surface of any spherical conductor is KQ upon R square, where R is the radius of the spherical conductor. Now electric field on the surface of conductor A is KQA upon RA square, and on the surface of B conductor, electric field is KQB upon RB square. Now EA upon EB is equal to QA. K will get cancel out and we will left with QA upon QB into RB square upon RA square. And we know that QA upon QB ratio is 1 by 2 and RB upon RA ratio is 2. We have done it before. We have found the ratio QA upon QB is 1 by 2. Also RA upon RB is 1 by 2. So here QA upon QB is 1 by 2 and RB upon RA is 2. So we will left with RB upon RA, which is 2 by 1. We can solve this. So this will become this. Means this QA and QA upon QB and this RB square upon RA square. RB, RA upon RB and QA upon QB. QA upon QB is 1 by 2. RA upon RB is, or RB upon RA is 2. So this will become 4. This will become 2, 1 by 2. So the final ratio will become 2:1. Got it. Okay. Next question. If two charges Q1 and Q2 are separated with distances d and placed in a medium of dielectric constant K, what will be the equivalent distance between the charges in air for the same electrostatic force? Okay, we have placed two charges in a dielectric medium of dielectric constant K and the distance between them is d. So we will find the electrostatic force between them. Now what is being asked here, that what will be the equivalent distance between the charges in air for the same electrostatic force. Now the electrostatic force should be same as in this case dielectric. Now we are removing the dielectric and placing the air between two charges. Now what is the equivalent distance? By how much distance apart we should place these charges so that the electrostatic will be same as the case one? Your options are d root k, 2d root k, 1.5 d root k, k root d. So I will give you some time to think or review the question. Okay, the correct answer is A, d root k. So what is the solution? Using concept 16.4, initially charges are placed in a medium of dielectric constant. As we have given that initially charges are being placed in the medium of dielectric constant K, and the force between them is, electrostatic force between them is Q1 Q2 upon 4 pi epsilon d square. epsilon, we are not using epsilon naught here. We are using epsilon, which is equal to K into epsilon naught. Epsilon naught is the permittivity of free space or vacuum. Permittivity in vacuum or air. And K is the dielectric constant. Epsilon is equal to K into epsilon naught. So what is the electrostatic force between two charges when they are placed at d distance apart, and the medium of dielectric constant between them is this K, dielectric constant K. Now mark this as equation 1. Now K is epsilon by epsilon naught. This is the definition of dielectric constant, that is the ratio of dielectric constant of medium is the ratio of permittivity of that medium upon permittivity in vacuum or air, or can say permittivity of free space. So without dielectric, this is with dielectric. Now without dielectric, when placed in air, force between the charges is, let's suppose we are now finding the force between two charges when they are placed in air, that is F prime equal to 1 by 4 pi epsilon naught Q1 Q2 upon R square. R is the new distance now, which we have to find, equivalent distance, which we have to find. So mark this as equation 2. Now on dividing equation 1 by equation 2, we get F by F prime is equal to 1 by K, dielectric constant, into R square by D square. Now we have to find R here, and we have been given the condition that for the same electrostatic force as in the case 1. So for same electrostatic force, F and F dash should be same. So F is equal to F dash. Now we get 1. F by F dash. If F equal to F dash, then the ratio of these two become 1, equal to R square upon KD square. Now R square is KD square, and R, we got the answer. What is the equivalent distance? What is the equivalent distance? R is D root K. D is the initial distance when two charges are placed in dielectric constant. So we got the answer. I hope you understood. Let's move to the next question. Consider the force F on a charge Q due to uniformly charged spherical shell of radius R, carrying charge Q distributed uniformly over it. When one of the following statement is true for F, if Q is placed at a distance R from the center of the shell. Okay. Now consider force F on a charge Q due to uniformly charged spherical shell of radius R carrying charge Q that is uniformly distributed over it. Which of the following statements, now you have to see which of the option is correct. Okay. First option is F is equal to 1 by 4 pi epsilon naught Q, capital Q, small q by R square for R less than R. Means for a distance which is smaller than radius of the sphere. That is, they are giving in this option the value of force inside the sphere. And this is force. Second option is force is between 0 and this value 1 by 4 pi epsilon naught Q by R square for R less than R, which is again the same condition for a distance less than the radius of the spherical shell, means inside the spherical shell. C is F equal to 1 by 4 pi epsilon naught Q by R square for R greater than R, means for a distance greater than the radius outside the spherical shell. And F is equal to 1 by 4 pi epsilon naught Q by R square for all the R, for any R. inside the spherical shell, outside the spherical shell, or on the surface of spherical shell. This is the value of force. This is the option 4. So now I will give you some time to think about it. So the correct answer is C. F equal to 1 by 4 pi epsilon naught q by r square for r greater than capital R. Means the distance greater than the radius of the spherical shell. Means for a outside point, the force is given by this expression. Now we know that in spherical shell, inside the spherical shell, electric field is 0. So if electric field inside a spherical shell is 0, the force must also be 0. So for a point inside the spherical shell, the value of the force is 0. So let's see solution using concept 7.4.4. For spherical shell, electric field is 1 by 4 pi epsilon naught q by r square if r is equal to or greater than r. Means electric field, value of electric field is 1 by 4 pi epsilon naught q by r square for the point at the surface of spherical shell or the point outside the spherical shell. This is the value of electric field for this condition. And electric field is 0 for point inside the spherical shell, which I have already mentioned. So force on charge in electric field. So force is due to electric field. Now we know that force is equal to Q into electric field. Charge. This is the charge which experience the force. Okay. This is the charge which experience the force due in the electric field of E. Now F is 0 for R less than R because the electric field is 0 for R less than R. And if electric field is 0 for R less than R, then force is also 0 for R less than R. And the force is 1 by 4 pi epsilon naught capital Q small q by R square for R greater than R. Okay. So I have not applied equal to here because there is generalized term which is R, small r. So this is 1 by 4 pi epsilon naught q by R square for R greater than equal to R. Because the electric field, value of electric field for R greater than equal to R is this. So force is Q into E. So Q into this value is E for R greater than equal to R. I hope you understood. Okay. Next question is, two identical metallic spheres A and B, when placed at a certain distance in air, repel each other with the force of F. Another identical uncharged sphere C is first placed in contact with A and then in contact with B and finally placed at midpoint between the spheres A and B, the force experienced by the sphere C. Now two identical metallic spheres are there, A and B, which are charged. And now another identical uncharged sphere C is first placed in contact with A and then in contact with B and finally placed at midpoint. Now we have to find the force experienced by sphere C, that is net force experienced by C due to A and B both. Now A and B initially repel each other in air. That means the charge, the polarity of charge on A and B on both the charges is same. Either they are positive charges, either they are negative charges. Options are 3f by 2, 3f by 4, f or 2f. So take some time to think about it. Okay, the correct option is B, 3F by 4. Solution using concept 4.1.1. Consider two metallic spheres A and B and both have charge Q. So, polarity of charges on both the spheres is same. So, by default, we are considering it as positive charge and both have charge Q. The force between two spheres will be F equal to KQ square upon R square. This is the F. Initial force when C is not there, the force between two charges is KQ square by R square. R is the distance by which they are apart. Now, this is the diagrammatic representation. This is A, this is B, and they are separated by distance R, both having charges Q and Q. This is the force between them. Now, when sphere C is placed in contact with A, now we know that any uncharged conductor placed in contact with any charged conductor, metallic sphere. So, the charge will transfer to the uncharged conductor. Since it is uncharged, another is charged with Q charge, so half of the charge will get transferred. By which concept? The potential on both the spheres will become equal and they are in contact and they are identical and radius of both the charges are same. So charge should also be same. Means if there is one metallic sphere with charge Q and other with zero charge, the charge after the contact of both the spheres will divide into half. Half will remain with the first charge conductor and half will transfer to the uncharged conductor. Condition: both the spheres should be identical. Non-identical spheres have not this type of distribution. For identical, half of charge will get distributed and charge becomes equal on both the spheres. So when sphere C is placed in contact with sphere A, charge on sphere A and sphere C will be Q by 2. Charge on sphere A is initially Q and charge on sphere C was 0. And after contact, charge on both the spheres become Q by 2. Now, sphere C has Q by 2 charge and A has also Q by 2 charge. Now, sphere C is placed in contact with sphere B. Now, sphere B has charge Q and C has charge Q by 2. Now, the charge will get transferred from B to C and try to equalize. So, in equilibrium condition, when the potential becomes same, since they are identical spheres, so the charge become equal on both the spheres. So, charge on B is Q and C is Q by 2. Now, the charge becomes half of the net charge, which is charge on sphere B and sphere C will be Q plus Q by 2. Q is on B, Q by 2 is on C upon 2. That is 3Q by 4. Now, after contact, the charge on both the spheres B and C will become 3Q by 4. Now, this is a diagrammatic representation. C is placed here. A having charge Q by 2, B having charge 3Q by 4, C having charge 3Q by 4. Now, F1 is the force experienced by C due to B. Because they are Q, these charges are of same polarity, so B will repel C in this direction. So F1 is the force due to B on C and F2 is the force due to A on C. Now F1 is K Q by 2 3Q by 4 upon R square by 4. So F1 is the charge. Now F2 is K 3Q by 4 upon r square by 4. Now we have found F1, F2. The forces on C due to A and B, both. You can find F2 first and F2 afterwards. Order can change. The force experienced by sphere C. Now, net force experienced by sphere C is F prime. That is the net force experienced by sphere C, which is F2 minus F1, which is equal to K 3Q by 4 minus K Q by 2 upon R square by 4 into 3Q by 4. After solving, we will get 3kq square upon 4r square, and initially we know that kq square upon r square is the force between two charges when C is not there. Kq square upon r square is the force between two charges when C was not there. So this was F. So 3 by 4 F is the correct answer. I hope you understood. Now move on to the next question. Two identical positive charges Q each are fixed at a distance of 2 alpha apart from each other. There are two identical positive charges are there having charges Q and fixed at distance 2a apart from each other. Another charge Q naught with mass m is placed at midpoint between two fixed charges. For a small displacement along the line joining the fixed charges, the charge Q naught executes simple harmonic motion SHM. The time period of the oscillation of the charge Q naught will be. These are four options that are given: root 4 pi cube epsilon naught m a cube upon Q naught Q, root Q naught Q by 4 pi cube epsilon naught m a cube, root 2 pi cube epsilon naught m a cube upon Q naught Q, and a pi cube epsilon naught m a cube upon Q naught Q. So I will give you some time to think about it. So the correct option is A, root 4 pi cube epsilon naught m a cube upon Q naught Q. So now we will see the solution using concept 13.1.3. Force on charge Q is F is equal to K Q Q naught upon A minus X whole square minus K Q Q naught upon A plus X square. Means there is a charge at the midpoint placed. Q naught charge is placed at the midpoint of two identical charges Q, and we are giving it small displacement like this diagram. This charge is placed at this, and we are giving it small displacement x here. Now the force between these two charges will become kq q naught upon a plus x square, and these two charges will become kq naught upon a minus x square, because we are giving this charge a small displacement in this direction. So net force is the force due to this, the force between these charges, the force on this charge due to this, minus force on this charge due to this. Now after solving, we will get this type of equation: kq q naught 4ax upon a square minus x square whole square. Now we know that as x, we are giving very small displacement, so x is very much smaller than the distance between them. So we can neglect x here. So f will become k q q naught 4ax upon a square. We are neglecting x square, so a raised to power 4. Now cancel out a with this, a raised to power 4. We will left out with 4kx q naught q upon a cube. Now for simple harmonic motion, we know that force should be proportional to the negative of displacement, or the external force should be proportional to the displacement. So for simple harmonic motion, this relation holds. F equal to m omega square x. Now we will reduce this expression into this form. Now F is equal to this, and uh, uh, we will equate this equation with this. So except x, anything that is there is m omega square, means 4k q naught q upon a cube is m omega square. So omega square we will get this, and omega we will get omega equal to root 4k q naught upon m a cube. And we have to find the time period. We know time period is equal to 2 pi upon omega. So time period is 2 pi upon omega, and after putting the value of omega, we will find this value of time period, that is root 4 pi omega epsilon naught m a cube upon q naught q. So this is the final answer. Let's move on to the next question. Two identical tennis balls having mass m and charge q are suspended from a fixed point. Now two tennis balls identical having charge q and mass m are suspended from a fixed point by threads of length L. What is the equilibrium separation when each thread makes angle theta with the vertical? Okay, so four options are given. D equal to q square L upon 2 pi epsilon naught mg raised to power 1 by 2. D equal to q square L upon 2 pi epsilon naught mg root to raised to power 1 by 3. D equal to q square L square upon 2 pi epsilon naught m square g raised to power 1 by 3. D equal to q square L square 2 pi epsilon naught m square g square raised to power 1 by 3. So I will give you some time to think. So the correct option is B. D equal to q square L upon 2 pi epsilon naught mg raised to power 1 by 3. Solution using concept 4.12. So this is the diagrammatic representation. So when two tennis balls are attached with the thread and suspended like this, having charge q and mass m, their separation is, we have to find this D, equilibrium separation. So what is this? So this is the theta that this thread is making with the vertical, and this is the L, length of thread, and we have to balance the forces on this tennis ball, one tennis ball, which is, this is the okay, considering this tennis ball, the tension in this thread is towards the point of suspension, this one, tension. So we'll resolve this tension into two components, T cos theta and T sin theta. And this is the mg, weight of this tennis ball, and this is the kq square upon d square is the force experienced by this tennis ball due to this tennis ball. So now we will equate these forces. We will get T cos theta equal to mg, and forces due to charges is kq square upon d square. So T sin theta is equal to this kq square upon d square, that is electrostatic force between these two balls, tennis balls. Mark this equation as 1 and this equation as 2. Now from equation 1 and 2 we get tan theta equal to kq square upon d square upon mg. So we know that small angle, this is theta is a very small angle, so theta should be nearly equal to sin theta or nearly equal to tan theta. So tan theta should be nearly equal to sin theta, or which is from diagram we can see that d by 2l. What is sin theta here? Tan theta is approximately equal to sin theta, which is approximately equal to d by 2l from the diagram. So by putting these values, what we got for tan theta is kq square upon mg d square equal to d by 2l, and from here we got d cube equal to 2k q square l upon mg, and d is kq q square l upon mg raised to power 1 by 3. After putting value of k, which is 1 by 4 by epsilon naught, we will get this final result. So I hope you understood. Let's move on to the next question. Two charges, each of each equal to q, are kept at x equal to minus a and x equal to a on the x-axis. A particle of mass m and charge q naught equal to q by 2 is placed at the origin. If charge q naught is given a small displacement, which is this small displacement is much less than the distance between them along the y-axis, the net force acting on the particle is proportional to. So two charges that are placed at x minus a, and one is placed at x equal to a on x-axis, and one charge q naught equal to q by 2 is placed at the origin. That is, charge on this particle of mass m is half the charge as compared to other two charges, and if charge q naught is given a small displacement, that is y small displacement, which is much less than the distance of separation, so the net force acting on the particle is proportional to. So the options are y, minus y, 1 by y, or minus 1 by y. So I will give you some time to think about it. Two charges. Okay. So the correct option is A, y. And solution using concept 4.4. Now the net force is 2f cos theta. How it came? See this diagram. This charge q naught is placed at the origin initially. Now small displacement is given in the y direction equal to y. Small displacement is given in the along the y axis. Small y displacement is given, which is much less than the separation between them. So after giving small displacement, what is the force acting on this particle? F force. These two charges are identical, and the distance of this charge from these two charges is also same. So the force experienced by this charge is equal. So force experienced by this charge is equal. So F is force experienced by this charge due to this, and this F is force experienced by this charge due to this. Okay. So after resolving these two forces, this is F cos theta of this F. Also the F cos theta component of this F will come along this way, and F sin theta of this force will come along this way, and F sin theta of this force come along this way. F sin theta components of both the forces cancel out, but F cos theta components will add up. F sin theta component will cancel out, F cos theta will add up. So the net force on this particle is 2F cos theta. F cos theta of this F and F cos theta of this force. Total force 2F cos theta. Now the F net we have found out. F net is 2kq q by 2 into y upon y square plus a square raised to power 3 by 2. Now we know that this displacement is much less than the separation between them. So kq square y, we are neglecting this y square here. Now we will left with a cube. So now here we know that q is constant, separation is constant. So force net is proportional to which quantity here? This is constant, this is constant, this is constant. So net force is proportional to this y. So force is proportional to the small displacement that we have given. I hope you understood. So thank you for cooperating.